So I'm going to write some stuff down. You should probably write some stuff down too. Because I already know what I'm talking about. So when we did the lab, okay, the thing that was interesting about it was that because we were using the spring, okay, the force wasn't constant. As you compress the spring further, it pushes with more force, so you got this thing. Okay? This is why we needed to use the FT area, is because both the force and the time matter. But the FT area is a cool thing, but the way we're going to express it to make it slightly easier for us, instead of having to calculate the FT area every time, we're just going to use the average force, okay? Or if it's just one constant force, it'd just be the force. So the thing that's cool about this is if I take the average force, which would be the halfway point on there, the thing that's really cool about this, if it's a triangle and symmetry is your friend here, if I were to shade the area of this blue one here, how do you think the area of the blue one and the area of the red one compare? They're totally the same. So what we're going to do is, instead of using the FT area, well, we're still going to use the FT area, but we're going to use average force times and we're going to use the little delta t here, which is the time that the force lasts. So this is the average okay? So in essence, this is what you guys plotted. You did the force times the time that the force lasts. You plotted against a change in velocity. You got a nice linear relationship where, what was the slope then? The slope was the mass of your car, correct?
Yeah.
This is what we just came up with, true? All right? Therefore, when I look at this, if I write y equals mx plus b, the force times the time that the force is applied is equal to the mass times the change in velocity. That's the conclusion from your lab. You guys feel okay about that? So what this brings us to, okay, what this brings us to is but basically it brings us to a question, okay? I gotta get it to the ball.
I didn't know what the brick in your side was. Your phone was like
Oh, no.
All right. So,
Yeah.
so I have two balls here. They're roughly the same size. Do they look close to the same size? They do, right? This one's a ping pong ball. This one is a golf ball. What is different about them? There are two things that are different about them. What's one thing?
Different sports.
Say that again. They have different textures. That's a good thing. Different what?
It's hollow.
Yeah, this one's hollow. Good. What else? The masses are very different. Yes? Which one do you think is more massive? Right? Remember, mass is an object's resistance to change in motion. It's how much stuff. All right? So go like this. Feel them. Which one do you feel is more massive? Absolutely, right? Right? This one is hollow. There's not much to it. All right? And so, if I were to throw these, each with the same force that lasted the same amount of time, which one would have a larger change in velocity? If I throw them and it lasts the same amount of force at the same time, which one would have a larger change in velocity?
The golf.
I actually think it's the other way. Because which is easier to throw?
Ping pong.
So if I think about it this way, I'm going to apply the same force at the same time. The one with the small mass is going to have a large change in velocity. But the one with a large mass, what's going to happen? Oh, typo. It's a small change in velocity. It's like if you go to the bowling alley and you can only throw a certain speed, or you can only throw it with a certain amount of force. If you want to maximize your speed, which ball do you throw? The one with less mass. Because at the bowling alley, you're trying to get the biggest change in velocity, so you get the small mass will give you a larger change in velocity. If you throw with a large mass, it's going to give you a small change in velocity. Is that cool?
Yeah.
Now, Owen, can you come up here, please? Yeah. So I'm going to throw these to you.
Okay.
Okay. Let's go behind you, so we'll get it on video so people can see. Okay. You're going the wrong way. All right, so I'm going to throw this to you with a certain speed. Okay, ready? Got it? I'm going to throw this. Ooh! I got it. Whipped it. Sorry.
Okay.
That's it. That's perfect. All right. So, all right, throw them back. Okay. So which one's easier to get going and which one's easier to bring to a stop?
This one.
Absolutely, right? Once it's moving, it's easier to bring to a stop. Yes? Okay, now we're going to do it with, this is a pool ball. Pool ball.
Different sport.
Okay. Now this is a 2-inch steel ball bearing. Which one's easier to bring to a stop?
This one.
That's right. Oh my God. You do some serious band damage. All right, good. Thank you so much. So what we're going to do now is we're going to relate two ideas that we were talking about last week and this week. So one of the things we were talking about was this. Didn't we calculate the m delta v for our carts when we were crashing them together? Do you remember that? Well, here's the thing. This, we called it the motion quantity. This motion quantity, which we called mass times velocity. This is a measurement of how hard it is to bring an object to a stop. Okay? The motion quantity is a measurement of how hard it is to bring an object to a stop. If an object has more mass, it's going to be harder to bring to a stop. If you throw it harder, it's going to be harder to bring to a stop. True? Does that make sense to you guys? Like conceptually? Well, here's the nice thing about this. We don't have to call it the motion quantity because it already has its own name. This thing that we're already talking about is called momentum. Momentum is a physics term that is a measurement of how difficult it is to bring an object to a stop. And it's really just the mass times the velocity. Now, if you want to calculate it, you just literally do m times v. We use the letter P. We use the letter P to represent momentum for a reason that I will make clear for you in a little bit. But this is what momentum is. Now, the problem with this, as a general rule, is that in our everyday language, we don't use the term momentum in a way that's consistent with our physics language. So we hear momentum in a couple different contexts. One context we hear it in is, let's say, in a sporting event. One team is losing, and then all of a sudden they start winning, and what will the announcer tell us about the teams? Oh, there's been a change, a shift in the momentum. Like, all of a sudden one team was losing, and now they're winning, and somehow this understanding of the momentum has changed. But that doesn't really have anything to do with the physics definition of momentum. Oftentimes, we watch a lot of American Ninja Warrior at home, and they'll say, oh, his momentum carried him over the gap. Well, momentum is a mathematical idea or a conceptual idea. It can't do anything. Or we hear it most often, like he didn't have enough momentum to get over. But what they're talking about is he didn't have enough speed to get over. Like, let's say you had to jump. Okay, so you're on a ramp, okay, and here's a ramp on the other side, and then down here there's some water, okay, and you're going to try to jump it on your bicycle. Okay, you're going to try to jump it on your bicycle. The problem is that in the water, there's of course there's sharks in the water. Okay. There's sharks in the water. So what happens is, if you're going fast enough, you might make it over, true?
Yep.
But what if you don't have enough speed? You're going to get eaten by the sharks, true? But what they always say the same thing. They always say like, oh, he didn't have enough momentum to get over. But what they really mean is he didn't have enough speed to get over, because you could increase the mass, would increase the momentum, but that's still not going to help you get over. Right? You guys with me on that? So when we talk about momentum in here, we're only talking about either the mathematical understanding or this conceptual understanding as a measurement of how difficult it is to bring an object to a stop. Sound good? Now, here's the cool part. What you guys did in the lab is you measured this m delta v. True? Well, think about the way this looks. If I want to change my momentum of an object, the mass stays the same, but what changes as a result?
The velocity.
The velocity. And so the change in momentum is the mass times the change in velocity. Because the mass of the object is the same, right? And then how do you change the momentum of an object? You take a force and you apply that force over some period of time. And so another way you can calculate the change in the momentum is the force, and this is the average force, times the time. And this is called, so the term they give to the change in momentum is the impulse. Okay? So the problem is impulse is an everyday word. Okay? impulse is an everyday word, but in the science context, it means the change in momentum. How do you calculate the change in momentum? Well, if you know the object and the change in velocity, you do it this way. But how do you change the momentum of an object? You take a force, and you apply that force for some period of time. In French, the word impulse, I think they took the P from impulse, and that's where they calculate the momentum. That's why it's P. It comes from the word impulse in French. But I don't know. I don't speak French, so I don't know what it is. I took some French in college. I don't remember learning a lot, but. All right, so I'm going to give this to you. And we're going to try to do, here, one is for you. You're so welcome. Take one. All right, let's see if we can't do the first couple real quick. We'll try to solidify some knowledge here. Let's see if we can't solidify some knowledge here. That'll be super fun. I'm excited about that. You're so welcome. All right, so work with your neighbor to do 1, A, B, and C, and then we will look at 2 in a moment. All right, work with your neighbor to get 1, A, B, and C done real quick.
Velocity, object A has 3 times the mass. Size of object B. I mean, momentum would change, right? Momentum wouldn't change, or it would, no. What did it ask? I remember this asking.
So it says 2 objects A and B have identical velocity, but A has 3 times the mass. So compare the momentum between A and B. Check with your neighbor. I'm sure your neighbor knows.
Okay.
How do you calculate the momentum of an object?
T equals MV.
Mm-hmm. And remember, if you need to reassess on something, let me know tomorrow, and I am happy to make that happen for you.
Yes. Okay. Let's give it a guess.
All right. So we have two objects, A and B. They have identical velocities, which means they're moving at the same speed in the same direction. A has 3 times the mass of object B. Okay? How does the momentum of A compare to the momentum of B? Peter, what do you think?
Object A has more momentum because there's more mass.
How many times more?
3 times.
He's money in the bank right here. He says, look, if it's 3 times as massive, it's going to have 3 times momentum. Because you'll notice that the exponents on each of these is 1. Therefore, if I triple the mass, I get triple the momentum. Good. 2 other objects, C and D, have identical masses. Object C has twice the velocity of D. Andrew, what do you think?
Object has twice as much momentum as mass.
Absolutely. C has twice the velocity. They have the same mass, so it has twice the momentum. Again, it's a linear relationship there. Okay? I like this one. 2 objects, E and F, where E has 4 times the mass, but 1/4 of the velocity. How do you think their momentums compare?
Is it the same?
They are the same. That's right. Again, linear relationship. So it's going 4 times as fast, but has 1/4 of the momentum, or 1/4 of the velocity, so the momentums are the same. Yeah, this is actually, momentum is such a great understanding of objects. Like, could a baseball and a bowling ball ever have the same momentum?
No.
They can. What has to be true?
Oh, the speed.
So the baseball, because it's so much less massive, would have to be moving so much faster. Right? All right, listen. You need to bring this sheet with you tomorrow. We're going to work on this in class tomorrow. All right? So you must have it with you. Do not ask me for one tomorrow. Okay? You are 16, 17, and 18 years old. I wouldn't even let my 10-year-old do that.
I'm not sure which one I do.